the whole point of the exercise yesterday was to now have something that we can relate to as we go forward. So I'm going to be making references to this as we try to answer the questions that are on the backboard. Okay? So the three big questions are, what is calculus to begin with, all right? So, but then what can calculus do for you? Okay? And what is it good for? And who uncovered it? I like to use the word uncover rather than discover, because here's how I view the world of discoveries. Is that, well, let's put it this way. You ever go to the beach like at Devil's Lake? You might have been to Devil's Lake. Okay. You ever see the guy with the metal detector walking around? All right. So what is he doing? He's finding stuff that's not seen. Okay. It's under the sand. And that's how I view all the mathematics that has ever been discovered, is that it's actually always been there. It was just somebody had to start digging at a place that seemed like, okay, I think there might be something here. And as they dig and dig and dig, they uncover what is already existing. Calculus was always there from the beginning of time. But it's up to us to try to uncover this. It's sort of like cures for cancer. It's out there. We just have to be the ones that uncover it. Okay? It's almost playing like a hide-and-seek game. And we got to outsmart it.
What would you define as a discovery then?
I don't know. I never really thought of that. A discovery. I guess people say like Columbus discovered America. It's kind of the same thing. Maybe they mean exactly the same thing, but I like to use the phrase uncovered better.
Okay.
That's all. All right. So let me see if we can wrap up what we did yesterday. So we took and we launched these. We launched it. Now, you got to remember that how we view things here really matters. If this is me, and I'm going to actually just put it, say, right at the ground, and we launch it, does everybody agree that the path that it takes is a parabola? That must be a defined fact. Okay, that was uncovered years ago. But this is the path that it took if we looked at it from the side. Okay, where we would say, look at what I'm going to do here. Feet here and feet here. This is a side view. Okay? That's the view from the side. If we could watch the whole thing, we could see the whole arch take place. Okay? That's not what we're going to look at. Okay? We're going to look at it feet with respect to time. Okay? So keep that in mind. This is from the side view. So what we're going to look at is, we're going to say, as time goes on, what's happening to the height of the ball. Okay? So, I think I said yesterday I wanted to do one where we launched it directly up. Okay, we actually did it in the second class. So I stood there in the center of the courtyard and I just launched it straight up. Okay, didn't have it come down. It came up a little bit of ways for me. It was a good thing. And so the side view of that was like this. This is the side view. If you just watched it from the side, you saw it go up, and then you saw it come straight down. Okay? That's what we're going to analyze. This is a really bad graph, but if you break it up over time, what happened was We launched it here. This is the height that it was at any given time, and then we have our final time. Now, I looked at all of the things, and I'm gonna use 8 seconds as the amount of time that the ball was in the air. Okay, looking at all of them, I'm going to use 8 seconds right here. Okay, turn to my picture book, your calculus picture book. So, you should have, turn to the page that looks like this. And aside from the numbers down here and the units right here, would you agree that if we could freeze frame the ball when it was in flight, that this is what the ball looked like? Okay. Now, natural occurring thing, you throw something in the air, this is what happens. How come the balls are so close together right here? And how come they're so far apart here? Yeah.
The acceleration is really strong, like right from the start, and then on the way back down, it's big acceleration again from the
Okay. So is the acceleration different as I move up? Okay. The speed, or rather, the velocity. Okay. So if we say the velocity, what's going on here is the velocity comes out as strong as it possibly can, right? And it starts to slow down. So the ball starts to slow down immediately after it launches. Okay? Now remember, this is what we're looking at it over time, but this thing is actually going up and then it's coming down. Okay? Two different perspectives. So it starts to slow down immediately as it gets launched. Okay? And then as it comes down, it's continuing to slow down. So, a couple of things. I wonder if we can figure out how fast it was going when it launched. That'd be kind of cool. That's something we can do with calculus, and we're going to do that with this problem. I'm going to tell you how fast that ball was coming out, just with the little data that we have. We can also tell how high the ball went. Okay? But we don't need calculus for that one. And then we can figure out how fast was it going when it hit the ground. These are the things that we can answer with calculus. And if we get the concept down, then we can apply this to only like a bajillion different places. This one just happens to be with velocity and acceleration. And then we'll have further conversations about what it means to have acceleration and all that after we get some answers. All right, so a couple of answers to what's up on the board. You can write this down. I'm not going to write it down. Calculus is the study of rates. Calculus is the study of rates. You can also say that calculus is the study of rates of change. Which means really that we're going to study slopes all year long. That's what we're going to do. In geometry, if you were to give a one-sentence thing for what's geometry, it's a study of shapes, isn't it? Boom, that's it. What's algebra? Study of equations and variables. Okay. Well, we're going to use geometry, we're going to use algebra when we do calculus, and we're going to study how things change. Okay. What is it good for? Well, there's really not a field that you can imagine out of every possible thing that people can study that you can't apply calculus to. Okay? Because anytime anything moves or changes, you can study it using calculus. Because if something changes, that means there was a rate that it changed by. And so there's an infinite number of places that we can apply it. And we'll touch on a bunch of them. And finally, who uncovered it? Well, the person who gets the credit is a guy I think you know, you've heard of, Sir Isaac Newton. Okay? It was in the 1600s. He's the guy that gets credit for it. But there's a whole bunch of other people that deserve the credit. Okay? First of all, there's a guy by the name of Wilhelm Leibniz. And Wilhelm Gottfried, we should put his name in there. And these two guys, Wilhelm Gottfried Leibniz and Sir Isaac Newton, both worked on solving a problem that was proposed by René Descartes 50 years earlier. And so they worked on it. And what's crazy about this story is both of these guys worked on it, solving the problem, at the same exact time. Leibniz was from Germany, and Newton was from England. And they both separately, at the same time, made the same discovery. It's pretty crazy. They both figured out exactly what I'm going to try to show you today. And the problem that they had is this. This is the underpinning of all of calculus. Go back to this right here. This is a position function. It's the height of a ball at any given time. And Descartes, most people don't know this, but I knew these guys when they were alive. And so Des, I used to call him Des. So I swing over by Dez's place, and he says, "Hey, Dr. J, what's up?" I said, "Nothing. How you doing?" And then we do the whole handshake thing, you know. And I said, "What are you working on?" He says, "Well, I've been throwing this ball up in the air, and I got a real problem." He says, "I think I got something here, but I don't really know what it is. I know it's in here somewhere." Because here's what he said. He said, "When I shoot the ball up in the air, I know it's going a certain speed. I know it's moving, okay? But I'd like to know how fast it's moving, okay? And here's what I observe. But I don't have the answer to it. I haven't figured it out yet." He said, "This is the plot of my ball as it's traveling. And this is what's known as a position function, because it tells you the position of the ball at any given time." Okay? And I'm going to put, like what we've got here, I'm going to change the units. I'm going to put feet. Let me do it again. I'm going to put seconds here and feet on the other one. Just kind of like what we have. I'm going to cross this one out. I'm going to make this feet. Okay? He said, "Here's my problem. If I know how high the ball is at any given moment," that one's actually a piece of cake. I can do that one. I can create a function that does that. But what I don't know is how fast it's going. But this is what I observe. Look at this. When the ball reaches the top of the peak, and I look at the slope of the line tangent to the graph of the position function, precisely at that moment, I'm going to draw a line tangent, and I get this. Okay? And I'm looking at that slope, and I say to myself, the slope of that line is what? It's 0. So wait a second. The slope is 0. And I know that when the ball reaches the peak, it comes to a rest. It stops before it comes turning around. So when it says this is at the top, I know that my slope is 0. Okay? That ball is not moving at that moment. I also know this. If I take a look at the slope of the line tangent to this function, right when I start, so if I'm going to try to draw a line, and the line has to touch this graph just one spot, okay? I'm looking at that slope and I say, that's a positive slope. Okay? So here the slope is positive. And as I move from the 0 mark to where this thing hits the top, and if I draw more of these slopes, whatever number I had here, whatever it was, I'll just make a number like 10. As I move towards the time equals 2 seconds, what's happening to the slope that used to be 10? It gets less. It might turn into 10, then 9, then 8, then 7, then 6, then 5, 4, 3, 2, 1, and then all of a sudden it's 0. Okay? I wonder if that has anything to do with how fast the ball is going. Because I know the ball slows down. And then not only that, if I go past the peak and I go down to this time equals 4 seconds, what do I notice about my slope here? Slope is negative. So, Des says, this is a really huge problem and I don't know how to solve it. What I really want to do is I want to find the slope of the line tangent to that curve at any x value. If I could do that, he actually said this. He said, this is not only the most important thing in the world of mathematics, it is the only thing that I ever desire to know. And then he died. And he never found out. Isn't that horrible?
How did you die?
I don't know. So look that up.
Weren't you there?
No, I was out of town. I was visiting Newton at the time, and I was saying, hey, you won't believe this, but Descartes got this thing going on here. And Newton said, you know what? He said, I got some time on my hands. I think I'm going to look at that problem. And so the handoff came from Descartes over to Newton, and Newton pursued this problem, and he actually figured it out. And I'm going to show you today how Newton figured it out. Okay? So let's try to solve Descartes' problem with trying to find the slope of the line tangent to a curve like this at any given time. Okay? So that's the goal. If we could do this, then we might be able to do this thing called calculus. All right. So here's what Newton said. And it was after a lot of work, too. He said, all right, I don't know where to start, but what I want to do is I want to be able to pick a point, any point, on a graph of a function, and I want to draw a line that's tangent to it. That means it touches just once to the graph. So the problem is I only have one point. Okay? And if I need the equation of a line that I can find the slope of, I need 2 points. Okay? Because, for example, they knew about slope because of Descartes' work, they said, okay, I know y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That's a formula for slope. But if both of them are the same point, you end up with 0 over 0, okay, which is nothing but a really big division sign. So he said, I don't know, let's do this. I'm going to pick a point A here, and I'm going to pick another point over here. I'm going to call it B. And I'm going to draw a line between those 2 points. Then the skies will turn blue. And so let's call this function, let's give it a name. I'll call it f. This is my f function. So I'm going to put a point here. I'm going to call this x. Okay. And I'll call this one. I'm going to do something weird here. What I'm going to say is, this is x. And then I'm going to say the distance between this point and this point is going to be called delta x. It's some distance. Okay? And so if that's x, this distance is delta x, that means this x position is x plus delta x. Okay? Now remember, this is the kind of class where you actually pay attention, you listen, you verify what I'm saying. Not like we're just going on and don't pay attention. So I need coordinates. What are the coordinates for this point? X is x. The y is f of x. You take the x, plug it into the function, and you get f of x. It's the y coordinate. It's y equals f of x. Okay, what are the coordinates for point B? X plus delta x. And then, what's the y coordinate? F of x plus delta x. Right? So, all I need to do is find the slope of that line, and then we can go on with some work. So, what is the slope of line segment or line AB? Slope of line AB, let's see here, is equal to f of x plus delta x minus f of x over x plus delta x minus x. Did I do that right? Y minus y over x minus x. Okay? This is the slope of this random line which contains these 2 points. Okay, can we simplify this at all? Yeah, x minus x on the bottom, I spy that. So f of x plus delta x minus f of x over delta x. That's what I got. Okay. Well, is this the slope of the line tangent? No. We should probably move that point B closer. Right? So if I shrink delta x to be a little bit smaller, I shrink it this way, I'm going to get another point. Okay? So I'll call this one, just for the heck of it, I'll call it B prime. This is B. I'm just moving point B over. So now delta x is this long now. Okay, it's a shorter distance. If I get closer to this, then I'm going to draw a new graph. And this is my new line. See? Is this slope closer to the slope of the line tangent to the curve? Yeah, it's closer than the last one. Is it a good estimate, though? Well, we just need delta x to get even smaller. Okay. So I could pick a new one. I'll call it B double prime. Draw another line. See what I'm doing? Draw another line. And then I could draw another dot. Each time I'm shrinking, I'm making delta x get smaller and smaller. Until I get really super close. Okay. Right now, if I find the slope of the line that passes through those 2 points, it's going to be a pretty good estimate for what the answer is, but it's not going to be exactly what the answer is. So if I get really super close, that is, I let delta x get really super small. Delta x is close to 0. As close to 0 as I can get without actually being 0. That's the key. I need some way to say I'm going to let delta x get really close to 0. Well, why don't I just let delta x equal 0? Because if it was delta x, we are allowed delta x to equal 0, then we'd be divided by 0. And we all know what happens when that happens. So, okay, so Isaac said this. That's what I called him. He wasn't a sir yet, because he didn't invent. He only got that after he discovered calculus. He said, Isaac, what do you got going on there? He says, well, here's my problem. I think I'm close. I have this ability to find the slope of the line tangent to this curve, except there's only one problem. Nothing's ever been invented yet that allows me to get really, really close to something, but I really don't need to know what happens exactly at that point. I need to invent something. And I said, just don't limit yourself. And so he said, aha, that's it. He said, I'm going to invent something new. And the thing that I'm going to invent is this thing called a limit. Okay? And the limit I'm going to abbreviate as lim. And here's my notation. I'm going to say the limit as delta x approaches 0, which means I'm going to let delta x get really super close to 0, but I know I can't let it actually equal 0 because I have to divide by it. And I'm still going to find the answer to whatever this division gives me, which is f of x plus delta x. And if I can do this, if I can somehow figure this out, then I will have a new derived formula. It would be a new derived formula from the original formula. So I have to give it a name somehow. A formula that's derived from another formula. Formula that's derived from another formula. Derivative. It's almost like a derivative of the formula. It's like it's almost on that poster right there. So I think I'm going to declare the definition of the derivative. And here's what it is. The definition of the derivative is the limit as delta x approaches 0 of this expression, which we often refer to as the difference quotient. It's a difference because we're subtracting, and it's a quotient because we're dividing. This is a secret formula of calculus. And it came about only because Descartes said, hey, I got this problem that I can't solve, but I think it has something to do with the velocity being connected to the position function on the graph. And after he died, Newton said, I'll take that and I'll advance it. And sure enough, he did. He invented this new thing called the limit, which now is going to allow us to find this formula called this derivative, which will allow us to find the slope of the line tangent to the curve at any given point, meaning that we can find the velocity of any projectile at any given moment in time when it's in flight. In fact, the reason why we were able to send a man to the moon is because of Descartes' question that he had back in the 1600s. The only reason why. No thought there, no original thinking there. You guys would still be using landline dial phones. Okay? It's really, we wouldn't be where we are if that hadn't happened. And what's really cool is Newton said this, if I see further, it is only because I stand on the shoulders of giants. You get what he's saying there? If you take a look at this right here, the work that each of these guys did was dependent upon the work that the people did before them. And intellectually, we can only get smarter by building on whatever it is in the past. And so he said, if I can see further, it's only because I stand on the shoulders of giants. And I said, hey, that's really good. You should write that down. There's an apple tree. Why don't you just go sit under that and write that down in your notebook? Okay. All right. So let's take the information that we have from yesterday's launch, and we're gonna try to develop some formulas from it. And maybe we'll use that thing to figure out how fast the ball was going when it left and when it landed. Okay. Yeah. Okay, we're going to use the 8-second flight. So here's what I want to know. So here's the problem. How high did the ball go? That is, what height did it reach? And we're going to put everything in feet here. Sorry to you physics people who like to use meters. Personally, if I had my way, we would have switched over to the metric system a long time ago. It's so much better to use. Okay, I'm going to need your help on this. So I'm going to plot our graph 1, 2, 3, 4, 5, 6, 7, 8. This is 8 seconds. We don't know how high this went, but we know that this is the height here. You're going to want to write this one down. You want to jot this one down. And this is in feet. Units are everything in calculus. All I know is this, it started on the ground and it ended on the ground, and at some point it reached its maximum. When did it reach its maximum? 4 seconds. Sounds good to me. Do we have any justification for that? Huh? It's halfway. Halfway and it sounds good. It's parabolic, right? Parabola has y-axis symmetry, and so even if we shift it over, it's still even. So the left side has to equal the right side, and therefore halfway in between is where it hits. Okay, here we go. This is what I want to know. I don't know this. I need some help. See there? No? Oh. Where do I go from this? I know it went 8 seconds. How high did it go? Do we know anything that we can connect to this? I'll take it from anywhere. Yeah, Brendan?
Would it maybe have something to do with if we have 2.00 and 0.8, you can start with the delta x there?
Maybe. Maybe. We'll put that in our pocket. Okay, the t equals 0 and t equals 8, definitely where the function has its roots.
Depending on how much pressure you use.
Okay, and so we had different amounts of pressure. Let's isolate it down to just one specific problem. Okay, so this one here was 8 seconds. It was 70 pounds per square inch. But what do we know that we can solve? How to solve this problem? Do we know anything from anything in the past? You guys are smart. You got like what, 11 good years of schooling under your belt, Xander? Height of the windmill, okay. We'd have to go measure it. Yeah? Okay, there is a known constant out here. Gravity, okay. Gravity is, I should make you look it up. Somebody look it up. It's negative 9.8 meters per second squared. What's it in feet? Yeah, that one number. Okay, common sense. 9.8 meters. Okay, just generalizing. That's pretty close to 10 meters, right? Okay, 10 meters. How much is 1 meter approximately equal to? About 3 feet, right? About how many feet is 9.8 meters? It's around 30. The equivalent is negative 32 feet per second squared. Okay, I'm really confused. I never got that second squared thing. Why is it second squared? We're going to, yeah.
It's not fast. Your rate is changing every second. Your rate is meter per second, and then every second how much it's changing.
Yeah. Real quick, everybody. Okay. Acceleration. Acceleration is change in velocity over change in time, right? Velocity is measured in, if we're using feet and seconds, what is velocity measured in? Feet per second. So it's feet per second. That's the numerator. Over change in time, which just says seconds. So feet divided by seconds is feet divided by seconds squared. That's where acceleration's units come from. There's another really good graphical way that we'll take a look at. We at 23 today? Okay. 2-minute warning. All right, gravity is this. Does anybody ever remember seeing some sort of position function that looks like this? 1/2 gt squared plus h sub 0. You studied it last year and the year before. Okay? This is the position function. It's the height of an object at any given moment on any planet that has gravity that we can measure. T is the amount of time, normally we measured in seconds, and h sub 0 represents the initial height of the object. Okay? So for our problem, S of t is going to be 1/2 times negative 32 t squared plus h sub 0, which is negative 16 t squared plus h sub 0. This is the formula that we're going to use to see how high the ball went. This is a position function that you should know. And I'll run through the units here again. G is the acceleration due to gravity. T is the time in seconds. H sub 0 is the initial height. And S is how high the ball is at any given time. Yes?
Wouldn't the initial height kind of just not needed in this case, between 0.
If we look at it that way, yes. But we're not going to look at it that way. But that's a good